Welcome to our detailed exploration of polymorphism. In this video, we'll delve into the two main types of polymorphism, compile time and runtime. We'll start by defining compile time polymorphism, also known as static polymorphism, and see how method overloading allows for multiple methods with the same name but different parameters. Then, we'll shift our focus to runtime polymorphism, or dynamic polymorphism, and explore how method overriding enables different behaviors for methods based on the object's actual class. Finally, we'll discuss virtual methods and late binding, key concepts that underpin dynamic method dispatch. Ready to understand how polymorphism can make your code more adaptable and powerful? Let's get started. Compile time polymorphism, also known as static polymorphism, refers to the ability of a program to resolve method calls during compile time, primarily through method overloading and operator overloading. Method overloading allows multiple methods to share the same name while differing in their parameter lists, such as having various print methods for different data types like printInt and printString. For example, you might create a calculator class with overloaded add methods that accept different argument types like int, double, or float. Operator overloading, available languages like C++, permits standard operators e.g. plus, dash, to be used with user-defined types, such as overloading the plus operator to concatenate strings in a custom string class. While Java itself doesn't support operator overloading, understanding this concept in other languages enhances the grasp of polymorphism's flexibility and its broader applications in programming. Runtime polymorphism, also known as dynamic polymorphism, allows a method to behave differently based on the object that invokes it, primarily achieved through method overriding and inheritance. In method overriding, a subclass provides a specific implementation for a method already defined in its parent class, enabling it to tailor the inherited behavior. For instance, if a base class animal has a method makeSound, the dog subclass might override it to return a barking sound, while the cat subclass could return a meowing sound. A hands-on example could involve implementing a class hierarchy with the animal parent class and subclasses like dog, cat, and bird, each overriding the makeSound method. Polymorphic behavior further illustrates this concept, as an object can take multiple forms. For instance, a reference variable of type animal can refer to a dog object, allowing the method overriding to take effect at runtime. Demonstrating this polymorphic behavior in a program, you could use a parent class reference to invoke methods specific to child classes, showcasing the flexibility and power of dynamic polymorphism in action. In Java, all non-static methods are considered virtual by default, meaning they can be overridden in subclasses, enabling dynamic behavior based on the object type at runtime. This leads to the concept of late binding, where method calls are resolved at runtime instead of compile time, allowing for dynamic method dispatch. For instance, consider a speak method in an animal class that could be dynamically resolved based on whether the object is a dog or a cat. When you invoke the speak method on an animal reference pointing to a dog object, it will execute the dog's overridden version of speak, and similarly for a cat object. A hands-on demonstration of this concept could involve creating a class hierarchy where the animal class has a speak method that is overridden by its subclasses, allowing you to observe late binding in action as the appropriate method executes based on the actual object type at runtime. As we wrap up our exploration of polymorphism, we've delved into both its compile time and runtime dimensions. We began by defining compile time polymorphism, or static polymorphism, where method overloading allows multiple methods with the same name but different parameters to coexist in a class. We then transitioned to runtime polymorphism, or dynamic polymorphism, highlighting how method overriding in derived classes enables methods to be invoked based on the actual object type at runtime. We also discussed virtual methods and late binding, crucial concepts that facilitate dynamic method resolution and ensure that the most appropriate method implementation is executed. With these insights, you're now well prepared to leverage both compile time and runtime polymorphism to build versatile and efficient applications. Embrace these concepts to enhance your code's flexibility and responsiveness. Happy coding, and may your use of polymorphism lead to innovative and elegant solutions.